When a 6-foot water balloon ruptures, gravity doesn't immediately take over. For a fraction of a second, the water hangs in midair, preserving the exact shape of the balloon that used to hold it. The human eye is physically too slow to process the mechanics of a liquid explosion like this in real time. By the time your brain registers the pop, the water is already pooling on the ground. Seeing this hidden world requires specialized hardware, like the Phantom Flex 4K. It's a cinema camera capturing 1,000 frames per second at 4K resolution. Operating equipment at this scale isn't as simple as pressing record. Pushing digital sensors to these speeds forces filmmakers to confront extreme physical constraints, involving light sensitivity and continuous data throughput. To successfully capture these moments, a filmmaker has to deliberately engineer workarounds for 3 specific roadblocks: light, data, and motion. The first roadblock is illumination. When you shoot at 1,000 frames per second, the camera's shutter is only open for a fraction of a millisecond. That tiny window naturally plunges the footage into darkness. The solution is volume. Operators have to flood the subject with massive 2,000-watt artificial lights, or shoot outside in direct, bright sunlight. But artificial lighting introduces a technical flaw. At extreme speeds, a high-speed sensor will record the rapid cooling of a standard light filament. To the naked eye, the room looks bright, but to the camera, it's a violent, unusable flicker. Filmmakers also have to follow the 180-degree rule to maintain natural motion blur. This dictates that the camera's shutter speed must stay at exactly double the frame rate. When shooting in bright sunlight, keeping that specific shutter speed lets in too much light. Operators use neutral density filters to physically block excess photons from hitting the sensor without changing the motion blur. Mastering high-speed light means precisely controlling flicker and exposure so the physical limitations of the shutter don't ruin the shot. The second roadblock is storage. Recording 4K video at extreme frame rates generates a massive volume of data that would instantly crash a standard hard drive. To manage the bottleneck, high-speed cameras use loop mode. Instead of writing to a permanent disk, the camera sends the video signal straight into a temporary memory bank called RAM. This memory operates as a continuous circle. The system deletes the oldest frames to make space for new ones, spinning in an endless loop. An operator presses a trigger to stop the loop, locking the data safely in the memory buffer before it is overwritten. Once the frames are trapped in the RAM, the operator transfers that temporary data onto a high-speed SSD like a Cinemag to save it permanently. This workflow allows an operator to react to an event after it's finished, effectively retrieving the previous few seconds from the memory buffer. The third roadblock involves the subject itself. High-end lighting and storage are only useful if the physical subject is moving fast enough to warrant high-speed capture. Scale determines your settings. Wide shots require lower frame rates to feel natural, while extreme close-ups of fast action require the maximum frame rate to maintain dynamic energy. Because transferring data from the RAM buffer takes several minutes, rehearsal is mandatory. Stunts or explosive actions must be perfectly timed before the operator triggers the camera. Operators often physically move the camera while the action occurs. This movement has to be accelerated to amplify the cinematic tension once it's played back in slow motion. This diagram illustrates how this technology is adapted for live events. The camera splits its output, providing a continuous live feed for the broadcast, while simultaneously playing back the high-speed recording for a replay. High-speed cinematography is a highly choreographed collision of extreme motion, data management, and perfect timing. Extreme slow motion is a deliberate engineering feat designed to navigate the physical limitations of light and time. You don't need a massive budget or a professional cinema camera to apply these physical workarounds. For smartphone users, solve the light problem by shooting in bright sunlight. Use the manual controls to underexpose the shot slightly so white surfaces don't wash out in the highlights. Then find a fast-moving, dynamic subject and set your phone's camera to 120 or 240 frames per second. With the right lighting and a fast enough frame rate, the hardware needed to record high-speed action and reveal hidden physics is already in your pocket.